Hi guys, I'm Rob and welcome to this, our second lesson in trigonometry. And in our first lesson, we spent a bit of time talking about solving right-angled triangles using Pythagoras' theorem. What we're going to take a look at in this lesson is solving right-angled triangles using the sine, cosine and tan ratios. And these ratios are based on the fact that in a right-angled triangle, when I know I'm dealing with a right-angled triangle as we dealt with in lesson 1, the three sides can be named as the opposite, adjacent and the hypotenuse, and then I can form ratios by dividing one of those sides by one of the other sides. The reason why we're forming ratios by dividing, we'll kind of mention in a moment, okay? But the key thing is that if the triangle is right angled, I can name the three sides: the opposite, the adjacent and the hypotenuse. So if you were to have a triangle that looks like this, we've got a right angle triangle with the three sides P, Q and R. I've got the same triangle drawn twice here. If I were going to name the sides, as we mentioned last week in the first lesson, the side opposite the right angle is always the hypotenuse. It's referred to as the hypotenuse, and that will never vary. So if this is the right angle here, the side opposite that, so P is the hypotenuse here in this case, right? Now, which of the other two sides, the opposite and which is the adjacent, depends on which of the two acute angles in the triangle I'm working with in any particular question, any particular problem. So if I'm using this angle up here, if this is the angle I'm working with in any particular solution, then you can see this side here, or, is opposite that angle, as we met in the first lesson. So that would mean in this case here that or is the opposite, and then the final side here, Q, then, that's the adjacent. Remember, the adjacent is the side that's beside the angle that you're forming, all right? So in this case here, that's the adjacent, the third remaining side. So the three sides here, P is the hypotenuse, Q is the adjacent, and R is the opposite, okay? If I was dealing with the same triangle, but was working with this angle here instead, so instead of working with this angle up here, A, I was working with this one down here, then again, this would still be the hypotenuse. So no matter which of the two acute angles I'm working with, the hypotenuse doesn't change. It's always the side opposite the right angle. But the other two sides, you can see, will be labeled the other way around, because if I'm working with the angle B, this side here is opposite B. It's across from B. So this side here would be the opposite. And the side that's beside the acute angle B is or here. So that's the adjacent. So if a triangle is right angled, we can name the three sides: opposite, hypotenuse and adjacent. The hypotenuse will always be the side opposite the right angle. That won't change depending on which of the two acute angles you're working with. But which of the other two sides, the opposite and which is the adjacent, will vary depending on which of the two acute angles you're working with. And then once we've labeled the sides like that, we can then use them to form ratios. Okay, a ratio is essentially a fraction by dividing one side by the other. And the three ratios you will have encountered before, you remember, are the cosine, sine, and tan ratios. So the cosine ratio is the length of the adjacent divided by the length of the hypotenuse. The sine ratio is the length of the opposite divided by the length of the hypotenuse. And the tan ratio is the length of the opposite divided by the length of the adjacent. So they're the three ratios: sine, cosine, and tan. Okay, so cosine is adjacent over hypotenuse, sine is opposite over hypotenuse, and tan is opposite over adjacent. And how you remember that, I mean, you will have encountered mnemonics before, SOHCAHTOA, this amazing word SOHCAHTOA that isn't even a word. There are all kind of mnemonics you can use. Oh hell, another hour of algebra, which isn't particularly helpful because it doesn't remind you which ratio is which. Cats are happy sitting on hedges, sleeping on hedges, thinking of apples. There's lots of them there. I think with a bit of practice, you're not going to need any kind of memory aid to remind you what those three ratios are. So cosine is adjacent over hypotenuse, sine is opposite over hypotenuse, and tan is opposite over adjacent. Instead of depending on a mnemonic, a memory aid, it's worth just getting a bit of practice, so this is second nature. So I know which ratios I'm dealing with. So you'll notice in the case of this triangle here, all right, if I'm dealing with the angle A, if I wanted to write down what cosine A is, cosine A, remember, is adjacent over hypotenuse. So the adjacent here is Q and the hypotenuse is P, so that's Q over P. So the cosine ratio here is the adjacent over the hypotenuse. The sine of A then is opposite over hypotenuse. The opposite is or, the hypotenuse P, that's or over P. And then finally the tan of A, tan is opposite over adjacent, so the opposite is or and the adjacent is Q, so that's or over Q. So that's there the three ratios for the angle A. Just notice then for the angle B, if I was doing the same thing, so the cosine of B is adjacent over hypotenuse, that's R over P. The sine of B is opposite over hypotenuse, it's Q over P. And then finally, the tan of B is opposite over adjacent, it's Q over R. All right, and it's just worth highlighting for you here that notice that this one here, the cosine of A is Q over P, and the sine of B is Q over P. So the sine of B and the cosine of A are the same as one another, right? And you'll notice as well here that the sine of A is R over P, and the cosine of B is R over P. So again, the sine of A and the cosine of B are the same. So in any right angle triangle, these two angles here, when you ignore the right angle, these two angles here, they're both acute angles. They're referred to as complementary angles because complementary angles are two angles that add up to 90 degrees. Okay? And if you have two complementary angles like this in a triangle, you can see the sine of one is equal to the cosine of the other. So the sine of this angle is equal to the cosine of that one, and the sine of that angle is equal to the cosine of that one. So if two angles add up to 90 degrees, if they're complementary, the sine of one is equal to the cosine of the other. Again, it's not essential, I understand that, but if I've got that in my back pocket, again, it's another tool I can draw out when I'm trying to solve a problem that might again give me options, as we'll see a little bit further down the road. So when you're dealing with a right angle triangle, when you take the right angle out, the other two angles are both acute angles, and they add up to 90 degrees. So angles that add up to 90 degrees are referred to as complementary angles. And for any pair of complementary angles, angles which add up to 90 degrees, the sine of one will be equal to the cosine of the other, right? So for example, the sine of 20 degrees, I know will equal the cosine of 70 degrees, because 20 and 70 add up to 90, okay? I'm fairly certain the sine of 8 degrees and the cosine of 82 degrees will be equal, because 8 and 82 add up to 90, okay? So complementary angles add up like that. But the question I guess to address before we just do a question or two is, why are we dividing one by the other? Well, working with the ratios is based on this idea here. That if suppose I take this triangle here, this is a triangle that you will end up seeing quite a bit. Okay, that's one of your set square triangles. So one of the set square triangles in your geometry set is this one here. It's the 30, 60, 90 right angle triangle. So if you draw a right angle triangle with sides or with angles 30 degrees and 60 degrees here, if you measure the sides, this is 1, this is 2, and this is root 3. Okay, using Pythagoras theorem. So there are your three sides there, right? So if you can imagine taking that triangle there, putting it on a photocopier and enlarging it. So photocopy a much larger version of that triangle. So I blow it up on a photocopier to look like that, right? So obviously you can see here that because I photocopied it, the shape is the same. The shape hasn't changed. So the three angles in this triangle are the same as the three angles in this one. It's the very same triangle. It's just we've got a larger version of it. Okay? So we've got one's a larger version of the other. So what we're going to have the key idea with this one, all right, that suppose I was to measure this side here. And let's say that side there is 10. Okay, so that side there is now 10 centimeters compared to the original. You can see that obviously the setting on the photocopier is making the sides of this triangle 5 times bigger than the original. Okay, so we've got a scale factor of 5 here. So this side here is 5 times, this side here is 5 times bigger than that side there. That means the other two sides in this triangle will be 5 times larger than their counterparts in the smaller triangle. So if that's 1, this will be 5 times 1, which will be 5. And if that's root 3, this will be 5 times root 3 here. Okay? So you can see these two triangles are both the very same shape. Okay, the triangles are the very same shape, but one's a larger version of the other. The term for that, remember, is they're similar or they're equiangular. We'll meet that later on. So the sides in this triangle are different to the sides in that one. But if I divide one side by the other, the ratios don't change. So notice, if I, for example, let's take the sine ratio, for example. So the sine of 30 degrees in this triangle here, you can see, will be opposite over hypotenuse. So opposite 30 degrees, we've got this 1 here. That's the opposite. And the hypotenuse across the right angle, there's the hypotenuse there. Okay, so the opposite over hypotenuse is 1 over 2. So the sine of 30 degrees there is 1 over 2. Notice if we look at the bigger version, this triangle here, the sine of 30 degrees there is equal to opposite over hypotenuse. So the opposite is this side here, which is 5. And the hypotenuse is this side here, which is 10. See the way so it's 5 over 10, which simplifies to a half. So although the sides of this triangle are not the same as the sides of that triangle, the ratios between those sides, the answers you get when you divide one by the other, don't change when you make the triangle larger. So when you divide one by the other, the amount you've made the triangle larger by cancels, and you get back to the original ratio again. So no matter how big or small a triangle is, if it's got those 3 angles there, the relationship between the pairs of sides will never change. So if you had a real world problem, for example, you've got an enormous triangle with a 30-degree angle down here. If you knew what that distance was, you'd be able to work out what this distance was, because you know the ratio between them is the same as it is in that triangle there or that triangle there. So the reason we divide one by the other is because it means that no matter how big or small the triangle you're dealing with is, okay, it means that the side lengths will change. As you start making triangles bigger and smaller, the side lengths will change all the time. But what won't change is the answer you get when you divide one by the other. So no matter how big or small a version of this triangle you create here, if you divide the side opposite 30 degrees by the hypotenuse, you'll always get an answer of 1 over 2. Okay, it can't be anything else. So that's the principle of working with the sine, cosine, and tan ratios. So if you look at the first question then on page 14. Okay, so the first question here on page 14. Remembering again that this method only works for right angle triangles. So we've got this right angle triangle here. And that angle is marked as 44 degrees. This is marked as 15. And we're asked to find that side there. So as we mentioned in last week's class, remember, in order to solve a triangle, I need to know 3 things about it. And I've got 3 pieces of information here. That angle there, and the 15. And at least one of those pieces of information is a side. So this triangle is solvable. Okay? So because I know for sure the triangle is right angled, I can do this using the sine, cosine, or tan ratios. Okay? I couldn't use Pythagoras because although the triangle is right angled, to use Pythagoras I need to know the other 2 sides to use this one here. So I can't use Pythagoras here, but I can use the sine, cosine, or tan ratios. So the first thing I do is I name the sides. Okay? So you can see the 15 here is the side that's opposite the right angle, so that's the hypotenuse. Okay, that's the hypotenuse. And then remember, if that's 44 degrees here, then this side here would be the opposite. That's the one we're not interested in this question here. We don't know what the opposite is, nor are we asked to find it. So that's the side I don't care about in this question, but this one here is the adjacent. So the 2 sides we're working with in this particular question are the adjacent of the hypotenuse. So which of your 3 ratios uses adjacent over hypotenuse, or adjacent and hypotenuse? That's cosine. So only one of the 3 ratios uses those 2 sides. Now, there's no point in using the tan ratio here because the tan would involve using the opposite, which is not in play in this question. There's no point using the sine ratio because the sine ratio uses opposite as well, and that's not in play in this question here. So only one of the ratios will be using the 2 sides that you've got in this particular question. So because the 2 sides I've got here are the adjacent hypotenuse, the ratio I'm using is the cosine ratio. Okay, so if I write that down, cosine 44 degrees, okay, is equal to adjacent over hypotenuse, which is x over 15. Because I know that no matter how big or small the triangle you get, if you've got a triangle with a 44-degree angle in here, the ratio between these 2 sides will never change. No matter how big or small the triangle gets, the ratio between those 2 sides will always give the very same answer, and your calculator knows what that answer is. So all I'm going to do now is I'm going to multiply both sides by 15. To remove the fraction. So if I multiply both sides here by 15 like that, on the left-hand side, on the right-hand side, they will cancel. So I just get 15 times cosine 44 degrees is equal to x. And this I'll just pop straight into my calculator. Now it's well worth making sure when you're using your calculator here that just make sure your calculator is in degree mode. Okay, because you can see the angle here is given in degrees, so to make sure that you've switched your calculator to degree mode. If you're not sure how to do that, consult the calculator manual that we have on the website, okay, to make sure you're clear on how to do that. So make sure your calculator's in degree mode here, not radian mode, because the angles here are measured in degrees, and then pop that into your calculator. And it says to give your answers correct to 2 decimal places, so if I put that in my calculator to 2 decimal places, it comes out as 10.79, and that's my answer. So that side there is 10.79 units long, okay? Because there's no units of measurement given for this measurement, there are no units of measurement for this one either. If that was measured in millimeters, then so would this be, and so on, but that's my answer. So you can see the second one then, part 2 on the same page. Got your right angle that looks like that, or your triangle that looks like that. And this angle here is marked as 36 degrees, up there, all right? And this here is 12, and that side there is x. So again, it's a right angle triangle. I know 3 things about it. I can use my sine, cosine, or tan ratio. So again, name the sides. So this is the hypotenuse here. The hypotenuse is the one that has to sit this question out. It's the one we're not using here. We don't know what the hypotenuse is, nor are we asked to find it. So hypotenuse is the one that we don't need here. This one here, remember, is opposite the angle we're leading with. So that's the opposite there, x. And then this side here, 12, that's the adjacent. Okay, so the hypotenuse and the opposite are the easy ones to identify, and then the third one's got to be the adjacent. So again now, which of my 3 ratios uses those 2? Well, 2 of the ratios use the hypotenuse, sine and cosine. So those 2 ratios we're not going to be working with in this question because we don't have the hypotenuse and we're not asked to find it. The 2 sides in play in this question are the opposite and adjacent, and the ratio which uses those 2 sides is the tan ratio. So we'll write that down, that tan 36 degrees is equal to opposite over adjacent, which is x over 12. And again now, to remove the fraction from the right-hand side, we'll just multiply both sides by the denominator, multiply both sides by 12, like that. Okay, on the right-hand side, the 12s will cancel, and I just have x here. And then this is just 12 times tan 36 degrees. And again, that goes into my calculator, and that comes out at about 8.72 to 2 decimal places. So it might be worth just pausing the video there now and trying part 3 and 4 yourself. Just make sure you're able to do it. So here's part 3. So again, if I name the sides, this side is opposite of the right angle, so that's the hypotenuse there, 6. And then this side here, x, is opposite the 19 degrees we're working with in this question, so that's the opposite there. So it's the adjacent here that we're not using in this question, that the adjacent has to sit this one out. So the 2 sides in play here are the opposite of the hypotenuse. That means we're working with the sine ratio. It's the only one of the 3 ratios that uses those 2 sides. So I'll write that down. Then the sine of 19 degrees is equal to the opposite, which is x, over the hypotenuse, which is 6. We'll multiply both sides by 6 to remove the fractions here. And I get 6 times sine 19 degrees is equal to x. If I pop that into my calculator, I get about 1.95. Is my answer there. And then the last one, part 4, if I name the sides again, so this side here is opposite the right angle, that's the hypotenuse, that's the one that has to sit this question out. We're not concerned with the hypotenuse here, we're not asked to find it, nor do we know how long it is. But these 2 sides here, x is opposite of the 61, so that's the opposite there, and then this one down here is the adjacent. So again, opposite adjacent, the only ratio that uses those 2 sides and doesn't use the hypotenuse at all is the tan ratio. So it's the tan ratio we're using here. So the tan of 61 degrees is opposite over adjacent, x over 7.6. And if we multiply across by 7.6, multiply both sides by 7.6 to remove the fractions from the right-hand side, that'll cancel. And I just have x here is equal to 7.6 times tan 61 degrees. And again, that just gets popped straight into my calculator, and that gives me 13.71. To 2 decimal places. The question asked me to give each answer to 2 decimal places. Now, kind of the final tweak on that, if you look at the first question on page 15, okay, so question 2.2 part 1, looks the very same as the one we just did, right, like that. And you can see there's my right angle there, that's 9, that's x, and this angle up here is 38 degrees. So once again, it's a right angle triangle. So I know I can use the sine, cosine, tan ratio. I can't use Pythagoras because I'd need to know that side there to find x using Pythagoras theorem, but I can use the sine, cosine, and tan ratios. So if I name the sides, this one here is opposite the right angle, so that's the hypotenuse there. And then this side here is opposite the 38 degrees, so it's the opposite that we're not dealing with in this question. That's going to have to sit this question out, not concerned with the opposite. Okay, but 9 is the adjacent. Okay, so the only ratio that uses adjacent hypotenuse and doesn't require the opposite is the cosine ratio. Okay, so remember, cosine of 38 degrees is adjacent over hypotenuse, 9 over x. Don't just always assume the x goes above the line as I did in all the previous questions. Okay, just follow the ratio here. So the x is below the line here, and that just means there's an extra step. So in the case this one here, as I did in the previous question, to remove this fraction, to get rid of the x below the line, I'll multiply both sides by x, like that. Because on the right-hand side, they will cancel, so I get x times cosine 38 degrees is equal to 9. And now, to leave the x by itself here, I'll divide both sides by cosine 38 degrees. Okay, so if I divide both sides by cosine 38, you can see they're going to cancel on the left-hand side and leave the x behind. And if I put this into my calculator, 9 over cosine 38 degrees, I get about 11.4. This question wants my answer to 1 decimal place, so it's 11.4. So just be aware that when you're setting up the sine, cosine, or tan ratios like this, it's not necessary that the x be above the line in the ratio when you set it up. And if it is below the line, just an extra step here, you multiply both sides by the x first to get rid of the fraction on the right-hand side, and then divide both sides by whatever this guy here is to leave the x on its own on the left-hand side. So you can see the next question on that same page. Part 2. Same idea. We've got our right angle triangle like this. And the sides are, this is 17 down here. That's x. And the angle marked is this angle up here, 72 degrees. Okay, so again, right angle triangle. We know we have 3 pieces of information. We can solve this. So I'm going to use the sine, cosine, tan ratio again. Ratios again. So if I name the sides, this side here, that's the hypotenuse. That's the one we're not going to be using here. This side here is the opposite. It's opposite the 72 degrees. That's the adjacent. So again, the ratio we're going to be using is the tan ratio. So the tan of 72 degrees is equal to opposite over adjacent, 17 over x. So again, you can see the x is below the line here, so we've got that extra step. Okay, so I'll multiply both sides by x, like that. They'll cancel. And I get x times tan 72 is equal to 17. And then we'll divide across by this, divide both sides by tan 72 to remove the fraction on the, to remove what's attached to the x on the left-hand side. So whatever I do on the left, I've got to do on the right. So divide this side here by tan 72 as well. And then I get x equals, when I put this into my calculator, I get it's around about 5.5. Again, to 1 decimal place. The question asks me to give all of these to 1 decimal place. So again, it might be worth your while now just pausing the video there and just try parts 3 and 4, make sure you can do them. So here's part 3. So if I just name the sides there, so x is the hypotenuse, it's across from the right angle. 14.5, that's opposite the 52 degree angle, that's the opposite. It's the adjacent that we're not working with here. So the ratio that uses opposite hypotenuse is sine. So the sine of 52 degrees is equal to opposite over hypotenuse, 14.5 over x. Again, we'll multiply both sides by the x to remove the fractions. So that goes here. We get 14.5 on the right is equal to x times sine 52 degrees. And then if we divide both sides by this guy, we leave the x by itself on the left-hand side. So I'll divide both sides then by sine 52 degrees. Okay, they'll cancel on the left. You can just get the x by itself. And if I pop that into my calculator, I get about 18.4. Is the answer to part 3. And part 4, same idea. That's the hypotenuse. That's the one we're not using here. So opposite the 11 degrees, that's the 3.4. So that's the opposite there. And then that means x is the adjacent. And then the ratio that uses opposite adjacent is the tan ratio. So we can go with tan 11 degrees is equal to opposite over adjacent, which is 3.4 over x. So like the previous couple of examples, we'll multiply both sides by x to remove the fractions. Okay, we just leave the 3.4 by itself on the left. You get x times tan 11 degrees here. And then divide both sides by tan 11 degrees to leave the x by itself on the left-hand side. They cancel, we get x, and 3.4 divided by tan 11 looks to me like it's 17.5. Now, what you could have done in this one as well, again, if you're thinking options, you'll notice here that just have it at the back of your mind, that because I know these two angles here, okay, if I subtract 90 from 180, it means the other two angles have to add up to 90. So if I take 11 from 90, I know that that one up there is 79 degrees. Right? And you see if I use that angle there instead, wouldn't that mean that this is the opposite instead, and that's the adjacent instead? So what I would have said there is that the tan of 79 degrees is opposite over adjacent, x over 3.4. And now I've avoided that getting rid of the x below the line. So you've always got options there. It's entirely up to you. That will give you exactly the same answer. You can check that if you want to. So there's one final thing then. That's basically working with the sine, cosine, tan ratios. There's one fine little trick I just wanted you to throw into your toolkit. Okay, that's very, very useful when we start getting to more difficult trigonometry. Okay, when we're dealing with some questions where you're working with the trigonometric identities, you're using the trigonometry formulas to try and find values. Or when we're doing some differentiation involving inverse trig, which is very difficult stuff, this trick comes in very handy. The trick is kind of mentioned for you in your notes on page 13. And the idea is if I give you one ratio from a triangle, you should be able to find the other two without having to find the angle first. So do you see we've got the example there where we're told that, the example there on page 13, we're told that sine theta is 36 over 85. And what the question wants to do is says find what tan theta is without finding the angle. So if you know what the sine of theta is, can you find the angle? Remember, that's the Greek letter theta. That's generally used as the variable if we're dealing with angles in trigonometry. The same way we use x in algebra when we're looking for a variable, and we don't have to, we just tend to. We tend to use theta when we're trying to, as the variable when we're looking for angles in trigonometry, right? So if you know what sine theta is, can you work out what tan theta is? Well, the idea here is, remember what sine is. Sine is opposite over hypotenuse. So if sine is 36 over 85, that's going to be equal to opposite over hypotenuse, because that's what sine means. So remember, that's telling me that in this right angle triangle, the opposite is 36, and the hypotenuse is 85. So what that means now is I've got two sides of the triangle. So what does the triangle look like? Well, if I just did a very simple sketch of what this triangle looks like here, okay, there's theta there, all right, there's my right angle, and the opposite is this side here, that's 36. Where's the hypotenuse? Well, it's opposite the right angle, that's this one up here, that's 85. So when he tells me that the sine of theta is 36 over 85, that's what he's telling me. The triangle looks like this. It's a right angle triangle. Okay, the side opposite the angle theta is 36 and the hypotenuse is 85. Now he wants me to write down what tan theta is. And in order to find tan theta, doesn't that mean I require the adjacent? Because tan is opposite over adjacent. So I'm going to need that side there. Well, now think about that based on what we've done so far in trigonometry. How could I find that side there? Pythagoras. So if you're given one of the ratios from a right angle triangle, what he's actually doing is giving you two of the sides. And once you've got two of the sides, you can use Pythagoras to find the third side. And then once you've got the third side, you can write down either of the two ratios. So I want to find the adjacent here. Just call it A. The adjacent. Okay, so if I use Pythagoras again, where's the hypotenuse? Well, it's 85. So we've got 85 squared is equal to 36 squared plus A squared. This is just like we did in the first lesson. Move the 36 across. I get 85 squared minus 36 squared is equal to A squared. Just subtract 36 squared from both sides and then take the square root. Square root of 85 squared minus 36 squared is equal to A, and that comes out at 77, whole number. So this side here then is 77. And now that I know that, writing down tan theta is not a problem. Because remember, tan theta, we know, is opposite over adjacent. Okay, this is the opposite here. That's the adjacent that we just found there. So the tan is opposite over adjacent is 36 over 77. And that's my answer. Now, as I said, we're not going to be using this trick very much just yet. But again, when we're busy looking at the ratios, it's not a bad time to put this on your radar. It's a very useful trick to have in your toolbox further down the line. Again, when we encounter some difficult questions in trigonometry and differential calculus, it'll just give us an option, okay, an opportunity to save ourselves some heartache. So just to finish up then, if you look at the first question on page 16, so question 2, 3 there on page 16, it says if cosine theta is 105 over 137, can we find what sine theta and tan theta are? So remember, cosine is adjacent over hypotenuse. So that's going to be the same as adjacent over hypotenuse. So I now know that the right angle triangle we're dealing with, the adjacent is 105 and the hypotenuse is 137. So what does that triangle look like? Just a very simple sketch just for my own benefit here. So if that's the angle theta there, okay, the adjacent, remember the opposite right angle, that's the hypotenuse there, that's 137. This side here would be the opposite, that's when we don't know. And this here is the adjacent, that's 105. Okay, so that's what the triangle looks like. And in order to find sine or tan, I'm going to need the opposite. Because sine is opposite over hypotenuse, so I'm going to need that for the sine ratio. And tan is opposite over adjacent, so I'm going to need the opposite for this. And it's not hard to find that now using Pythagoras' theorem, as we've just mentioned. Okay, so to find the opposite there, remember the hypotenuse is 137. So 137 squared is equal to 105 squared plus the opposite squared. Subtract 105 squared from both sides. We get 137 squared minus 105 squared is equal to O squared, and then just take the square root like that. The square of 137 squared minus 105 squared is equal to O, and that comes out at a nice whole number again, that's 88. So this side here is 88. And now that we know all three sides, now we can write down any of the three ratios. Okay, the one we knew already was the cosine ratio, but now we can write down the other two. So remember to write down what sine theta is. It's opposite over hypotenuse, it's 88 over 137. And tan theta is opposite over adjacent, which is 88 over 105. There's my two other ratios. So remember, I haven't had to find theta. Now, what we will be able to do after the next lesson is we will be able to find that angle there. So I could find what that angle there was, and then just you calculate the ratios that way. But this way is better because it keeps everything whole numbers. If I tried to find that angle there, I'd probably be moving it decimal. So it's not wrong, but just it keeps everything a bit tidier if I can do it this way. So look at that question at the bottom of that page, question 2.4, just to start finishing up this lesson. It says if sine theta is equal to 0.6. Now, remember that when we're dealing with these ratios, they're fractions because they're one side divided by another. So I would turn that into a fraction. So if you put 0.6 into your calculator and press equals, it'll write that as a fraction. It's 3 over 5. Okay, so the decimal there, I'll turn it into a fraction first. Okay, because remember, I need to give me two sides of a right angle triangle. It wouldn't be wrong to put that over 1 and say the opposite is 0.6, hypotenuse is 1. It'll still give you the same ratios at the end. But as a simple whole number, fractions like that, a fraction like that, it's 3 over 5. And sine is opposite over hypotenuse. So the right angle triangle we're dealing with here, the opposite is 3, and the hypotenuse is 5. So again, if you sketch very quickly what that triangle looks like, just very simple sketch like that. There's the angle theta there. And the opposite, this side here is opposite that, that's 3 there. And this is the hypotenuse, that's 5. It's the adjacent we don't know yet. But it's the adjacent I'm going to need to write down the cosine and the tan ratios. So I have to find that. And again, I'll find that using Pythagoras' theorem. So 5 squared equals 3 squared plus a squared. So 5 squared minus 3 squared equals a squared. So then just take the square root of both sides. Square root of 5 squared minus 3 squared is equal to a. And that comes out at another nice whole number. That's 4. So a is 4. So again, now that I know all three sides, I now know the one side I didn't know from the start. Now I can write down my other ratios. So it wants me to write down what cosine theta is. So cosine, remember, is adjacent over hypotenuse. So it's 4 over 5. And tan of theta is opposite over adjacent, which is 3 over 4. Now, you might kind of say, look, I think what might be a better idea in the exam here, would it not be better to give that as 0.8? Okay, turn it into a decimal, and that is 0.75, because the original one was given as a decimal. Should I give these as decimals as well? It doesn't make any difference at all. Your answer is correct. The form doesn't matter. Okay, but they're the two answers there. So to finish up this lesson, if you maybe just pause the video there, try the two questions on page 17 to bring us up to the end of this particular lesson. So here's those last two questions then. So in question 2.5, it says that tan A is root 39 over 5. We're asked to find cosine A. So again, tan, remember, when he gives me the tan ratio, he's giving me two sides of a right angle triangle. In this case, it's the opposite and the adjacent. So what does that triangle look like in very simple sketch? So it looks like that. There's the angle A there. So the opposite is this side here. That's root 39. And the adjacent this side here, that's 5. It's the hypotenuse we don't know in this case. But it's the hypotenuse I need to write down the cosine ratio I'm asked for. So I'll find the hypotenuse there. So remember, the hypotenuse squared is going to be equal to root 39 squared plus 5 squared. And again, if I just take the square root of both sides there, right, like that, it tells me that the hypotenuse is 8. Just popping out to my calculator. So I know that this one here is 8. So now to write down the cosine of A, it's adjacent over hypotenuse, it's 5 over 8. That's my answer for that one. And then this one here is just, there's an extra little bit of head scratching in this one. Okay, again, just tying it with something we've already dealt with. So I'm told the cosine of B is 9 over 11. Remember, cosine is adjacent over hypotenuse. So that's adjacent over hypotenuse like that. So that means the adjacent in this triangle is 9 and the hypotenuse is 11. So what does that triangle look like? Well, there's the angle B there, my right angle there. And the adjacent, remember, is this side here. So the adjacent there is 9. The hypotenuse is 11. It's the opposite here is the one we don't know, but I will need the opposite to write down the ratio I'm looking for. Okay, so I'll find the opposite first. So using Pythagoras, 11 squared equals 9 squared plus the opposite squared. Subtract 9 squared from both sides. I get 11 squared minus 9 squared is equal to the opposite squared. And then take the square root of both sides, like that. And that comes out as a surd. That's 2 root 10. So this side here is 2 root 10. We went in our first lesson, we mentioned that if you get a surd answer, leave it like that unless you're told otherwise. To decimalize, that's 2 root 10 there is the third side. Now, he wants me to find cosine 90 minus b. Not cosine b, cosine 90 minus b. So just remember something that we mentioned earlier on in the lesson. Okay, that remember that if that's 90-degree angle here, that these two angles here add up to 90 degrees. So if this one's b, this one here is 90 minus b. Now that's the slightly trickier part of this question here, to recognize that the 90 minus b we're dealing with here is that angle up there. So we're trying to write down the cosine of that angle up there. Okay, the other angle in that right angle triangle is the one we're looking for, the one we're dealing with, all right? So to write down the cosine of that angle there, it's going to be adjacent over hypotenuse. So remember, from this angle here, that's the hypotenuse, that doesn't change. But if this is the angle we're dealing with here, this is the adjacent. Okay, so for the angle 90 minus b up here, that's the adjacent, that's the hypotenuse. So the cosine of 90 degrees minus b is adjacent over hypotenuse. It's 2 root 10 over 11. And that's my answer. So that's a quick look at working with the trigonometry ratios. So in our third lesson, which will be quite short, we're just going to take a quick look at using the inverse sine, inverse cosine, inverse tan to find angles in a right angle triangle, and that'll finish up our look at right angle triangles.